So today I'm going to talk to you about some of my work on mobile interaction. Much of this work is conducted with my interns over the past few years at Google. First, I want to ask you this question. How many times do you access your mobile devices per day?
200.
30,000.
So it turns out we access our mobile devices quite a lot. According to this report from KPCB, a major venture capital firm, mobile users on average use their smartphones about 150 times per day. These include making phone calls, messaging, and other typical activities we would do throughout the day. So clearly, mobile devices have played a very important role in our everyday life. So it's amazing how far computing technologies have come along. A typical smartphone today like Nexus 5, has more computing power than the computer sent Apollo 11 to the moon. But the way we can leverage this enormous computing power is quite limited for a number of reasons. So if we think about the mobile user interface today, they're pretty much structured based on graphical user interface concepts such as windows and menus. These were introduced 3 decades ago for desktop computers. These concepts are intuitive and easy to use in a setting that has a large display and precise input devices such as a mouse. So a big advantage of graphical user interfaces is so-called what you see is what you get. The functionalities of the system are actually exposed and accessed through their graphical representations. So a user can easily perform a target action by acquiring the corresponding graphical object. But the small form factor of mobile devices really limits the amount of information we can present on the display and what we can possibly acquire. So the input bandwidth is further constrained by the lack of precise input devices. For example, the target item has to be large enough for the finger to acquire, right? So as a result, the rich functionalities of the system often have to be presented through a deep hierarchy. So navigating this deep UI hierarchy requires a significant amount of visual attention and very precise motor control. So these are not affordable for a mobile user. So fundamentally, traditional user interfaces rely on the 2D coordinate of the final touch point and the target being acquired. This paradigm is intuitive, but it essentially ignores the rich semantics of user actions and behaviors. So these are potentially more effective for communicating what we want to achieve. So my research goal here is to push the boundary of what a computer system can possibly understand about user actions and behaviors to expand the interaction bandwidth of mobile devices. For the rest of the talk, I'm going to give you a few examples about our work in this area. So first, I'm going to show you how we can use hand-drawn symbols to access mobile devices. I will talk about how these gestures can carry rich interaction semantics and compelling interaction scenarios they can enable. Then I will talk about multi-touch input, the most important class of input behaviors on mobile devices. And I will discuss the fundamental challenges multi-touch input has raised to interactive computing and how we can address them using advanced tools. So in addition to looking at explicit user input, it's important to expand the interaction bandwidth by learning from user behaviors to optimize the UI in the background. For example, by knowing the user is shopping in the grocery store, we can better adapt the application for the user at that time. So at the beginning of the talk, I asked you how many times you access your mobile devices per day. So many of these accesses actually require the user to turn on the screen, unlock the phone, and navigate the deep UI hierarchy. So this additional effort is imposed on every task, almost every target task the user wants to perform, which I call heavy taxation on mobile access. To address these problems, we developed the system that allows the user to use gesture shortcuts to access mobile devices, actually from the standby mode. So here, let's assume we want to start the YouTube app on this phone. Before we even turn on the screen, we can draw letter Y directly on the touch screen. Oh, sorry, why it's not working. So the system returns a list of search results, and then we can click on YouTube. So that's how fast we can access our mobile device, such as launching an app. So this is cool, but as you have figured out, there are a few challenges to achieve this functionality. I'm going to talk about our solutions to some of these problems here. So for this to work, the touch screen has to be always active in sensing user input. So it's quite possible that the user accidentally touched the touch screen. For example, when the phone sits in the pocket, or when the hand accidentally touched the bezel of the screen while holding the device. So the first problem we need to address here is to be able to tell intended gesture input from accidental touches. To do this, we instrumented a set of Nexus 5 devices. We asked the participants to use these devices as their primary device for a few days. And we observed, on average, each user generated about 800 accidental touches. So that's a lot, right? More than what we would expect. Then we also asked the same group of people to draw character gestures in a variety of conditions, such as using the phone single-handedly or by manually, walking versus sitting in all these conditions. So based on this data, we're trying to understand how intended gesture input is actually different from accidental touches by looking at the signals from multiple sensors, such as the touch screen, the proximity sensor, and the accelerometer. Here, I want to give you a couple of examples about these analyses. So both accidental touch and the intended gesture input generate a sequence of points, which we call a gesture. Which we call a touch stroke, right? The heat maps here show how touch strokes are actually distributed on the screen. As we can see here, accidental touches are distributed almost uniformly on the screen, but the intended gestures are more concentrated at the center of the screen. So this is because accidental touches they occurred more randomly, but for intended gestures, the user tend to choose the center area of the screen for maximum flexibility. Just to clarify, here we use the farthest point on the stroke to the bezels as the location of the stroke. Right? So the difference of these two types of behaviors is also well captured by other sensors, such as the accelerometer. As we can see here, the acceleration change for intended gestures is actually quite small. It's because the user tries to keep the device very stable for drawing the gesture. But for accidental touches, that is not the case. So based on this analysis, we trained a decision tree model by combining a set of features. We achieved good accuracy in terms of precision and recall. Here I want to show you how well it actually works. So these accidental touches will not trigger any actions. But when the user draws a gesture, the system responds right away. That's how well it works. So because now we need to sense the user input all the time, battery consumption became a very important problem. Our current implementation can only last for a day because we need to keep the CPU running all the time for continuous sensor processing. But several modern smartphones have already adopted the architecture of using a low-power DSP chip to process continuous sensor input without waking up the CPU. But it's hard for us to access these co-processors. So to find out how the battery consumption of our system in such an architecture, we used an external approach by experimenting with our gesture detection code on this low-power DSP chip. It's the same chip that has been used by iPhone. So the experiment indicated that the battery consumption of our system is quite small, right? So both the high detection accuracy and the trivial battery consumption indicate that this always-on gesture approach is feasible. So far I have talked about how we can detect intended gesture input. So once the gesture is detected, we need to infer the target item the user wants to access. So there are multiple levels of ambiguity in this process. The system can misrecognize the gesture, or the user can misspell the keyword of the target. On top of these, it's often ambiguous which target the user wants to access given a character. For example, letter Y could be for different target rather than YouTube. So this process is achieved by a subsystem named gesture search. It addresses all these ambiguities both on the UI and in the underlying algorithm. I'm going to talk about this system a little bit. So gesture search allows a user to access a range of targets such as applications, contacts, and settings using gesture shortcuts, often numerical gestures. Here, let's assume we want to turn on Wi-Fi hotspot. Right? That's a task some of you probably do. So we can draw the gesture anywhere on the screen. So this design allows eye-free input. As we can see here, the gesture here looks like letter A or letter H, right? It's ambiguous to the system. So the system actually preserves this ambiguity by returning the search results that match either of these interpretations. At the same time, you can probably see that the original gesture is shown at the bottom of the screen. This indicates that the interpretation of the gesture is not determined yet, right? So at this point, we can scroll the list to find the target, or we can draw more gestures to ask the system to refine the search results. With these two gestures, the target tethering and the portable hotspot is shown at the second position. Now we can click on it and configure the hotspot. So internally, we use the single probabilistic model to capture all these levels of ambiguity. It encodes how input gestures can lead to different targets. Every time the user interacts with the system, it learns from the user behavior and by updating the probability distribution in the model. So gesture search is available on Google Play, and as we can see here, users respond positively to the system. I encourage you to try it out. So in addition to being a useful tool, we also observe some profound changes regarding user behaviors. As this user commented, I forgot to use menu after installing this app. So we really see the transition from the use of graphical user interfaces to gesture-based interaction. Another user commented, I gestured, I find it.
Sorry, just obvious thing that you could have also chosen to do, but you didn't. I'm trying to pick your brain to understand a little bit why. As soon as I unlocked my device, you could have automatically, like Android could just show a keyboard, and I could just start typing there, and it becomes basically a spotlight search over my phone, just like you did. Is there anything that was particular to why a drawn gesture, which has potentially, say, more ambiguity to it than something that's like a form factor that they're used to, like the on-screen keyboard?
So the question with turning on the screen, unlock the phone part, or it's with how you would, the choice between keyboard and gesture?
Well, I guess it's a little bit of both. You could have imagined I hit a single button, and what happens is a keyboard pops up. So there's no unlock screen. It's just sort of the unlock screen is a keyboard where I start typing what I want, like a spotlight search. And then that becomes the launcher. Like, at some level, I'm wondering, is this about having quick access to a launcher, or is it about the gestures themselves as the input modality that's really important?
I think it has to do with both parts. So the first part is the difference between keyboard-based interaction and gesture-based interaction. So gesture-based interaction, gesture input has the advantage of you don't need to acquire small targets on the display. So basically, the entire screen is what you can use rather than the small targets on it. So another thing here is with turning on the screen and unlocking the phone. These are additional steps we're trying to save. We're trying to avoid. Yeah, I think there are really two problems we're trying to address. One is to determine if the user wants to interact with the device. Once that's determined, then we need to figure out what the user wants to do with the device. That's the second part. I think this has the advantage compared to the traditional route. But
Okay. I'm curious for your opinion on this.
yeah, any other questions?
I routinely use my phone with either a slide-out keyboard or, depending on the, if I'm using one of my dev devices, a Bluetooth keyboard. Does the app currently allow for recognizing a key press on a physical keyboard and interpreting that as if it was an interpreted gesture and starting the search from that branch?
I'm not sure I understand the, all part of the question, but if you want to.
If I've got a physical keyboard, either as part of the phone hardware or connected by Bluetooth, currently it's already set up in Android OS that a press of a key on that keyboard will turn on the device. Does gesture search grab the input from this keyboard and turn that into the start of the search as well? Or does it only listen to the screen input, the touch screen?
Yeah, so technically it only takes touch screen input right now. Yeah. But it's an interesting thought. Actually, one project I did with my intern is to enable gestures on the keyboard even. Right, so if you slide your finger on the physical keyboard, we can also do gestures that way. So I think it's not exactly what you are asking, but it's kind of related. Yeah.
I have a question on the previous slide. No, one more. Not actually one more.
One more?
Yeah, one more. Yeah, when you update your search query, how can you distinguish like scrolling down the list from entering a...
Yeah, that's a good question. I skipped that part because I didn't want to go into too much detail. So basically, yeah, I think you're right. So there are two types of behaviors. One is you can scroll the list. The other one is you can draw gestures directly on top of the list. So currently, we're trying to differentiate what you're trying to do based on the trajectory of the gesture. So if you at the beginning when you slide your finger on the screen, it's really ambiguous to the system what you are trying to do, but it tries to make a decision as you slide your finger more. So simply speaking, if you are moving your finger up and down, it might interpret as scrolling. But if there's no more variation on the trajectory, it might interpret that as a gesture. So there are more details actually in the paper.
Maybe you could also have you could have a very short list, so there's no scrolling enabled.
Right. Yes. So that's actually quite reasonable. So another layout we had at one point on tablet is it's a grid layout. You don't scroll the grid, so there's no such problem anymore. Yeah. Yeah. So this slide actually partially answers your question. Justifies your idea about having fewer items on the screen. So basically, based on the large-scale data set I collected from millions of users, we can better understand the user behaviors and the performance with the system. So here I want to talk about a couple of these analysis. As you can see here, the position the user tends to click on obeys the typical power law distribution, right? With the top position accounting for over 60% of traffic. So come back to your question, we can probably just present 6 targets or 7 targets on the screen. That will probably be enough, right? So in general, the more gestures the user use for access, or in other words, the longer a query is, the more likely a target will appear at a top position in the list. So on average, it took about less than 2 gestures for the user to get to a target. So, so it's about a couple of strokes away. So that's quite compelling. And gesture search currently only uses the top item for the prediction based on user behaviors. About 46% of the traffic was actually completed by the prediction based on user behaviors.
So the fact that the median search position is 1 suggests that what's happening is I keep gesturing until the thing I want is at the top, even if it might exist, but it's lower.
Exactly.
Okay.
So that's actually quite interesting. We basically see 2 types of behaviors. Some users tend to draw more gestures to bring their target to the top position, right? So even the target is actually like a 3rd or 4th position, they don't want to click on it. They want to draw more gestures to bring the target to a top position. But some users, they tend to screw the list. They just draw 1 gesture. They're trying to find the target in the list. But the majority of the users trying to draw more gestures to access target. As one user commented, I don't care how many gestures I have to draw, my target will eventually show up at the top, right? So sometimes the time it takes is not the only important measure here. So it's about the dedicated attention you have to pay to the interaction. I think that's something, yeah. So at this point, you might be wondering if we can actually go beyond just the character gestures. How about a plus sign for Google Plus, or the cursive writing of NY for New York Times? So to support these arbitrary symbols for gesture shortcuts, one approach is that we can assign a specific symbol for each of these targets in advance. Then we can compare an unknown gesture with these templates based on how similar they are, right? So we can find the one that matches the best. So my colleagues and I developed a few algorithms for template-based recognition. So some of these have been used by a lot of researchers in the field for their simplicity. But one big problem with this kind of approach is that you have to define all the shortcuts in advance, right? So it's a non-trivial effort for the user to define and memorize these shortcuts. Then we ask the question, if we can infer the meaning of an arbitrary gesture without having the user to actually define these gestures. So it sounds like a mission impossible, right? So, but I want to test this with you. Can you guess the meaning of this gesture? What the user tries to activate?
Angry birds.
Angry bird. Really? Yeah! So you didn't see my talk before, right? Cool. Okay, one more test. How about this one?
Foursquare.
Foursquare. Exactly. So the fact that you can guess the meaning of these gestures does tell us something, right? I will come back to this later. So then to find out how users actually derive or perceive these gesture shortcuts, we did a study with 26 participants. We asked them to come up with gesture shortcuts for about 400 targets in whatever way they think appropriate. So these are some examples from this study, from this open-ended study. I want to talk about some important results from this study. So first, we see basically a mix of character and drawing-based gestures. right? With the drawing, so the character-based gestures being the dominant form. So this kind of explains why gesture search actually works, right? So it's using often numerical gestures. Another important result here is that we found quite a bit of commonality across the gesture shortcuts people define for different targets. So in this experiment, we're trying to recognize one user's gesture shortcuts using those have been defined by other participants. So as you can see here, we got some accuracy here, and the accuracy could be even better if we had more participants. So it's quite sparse actually in terms of the number of gestures we got for each target.
So this is saying that if I trained on a random other user's gesture, I would still get the right thing 20% of the time.
So we have 26 participants. We trained we used the template-based recognition by using 25 participants' data as a training sample. So we try to predict this last user's gestures, right? But all this data is collected separately, right? So yeah. So this kind of explains why you were able to guess the meaning of the gestures of those two examples I just showed earlier, right? So based on these discoveries from this open-ended study, we designed a system to infer the meaning of arbitrary gesture the user draws, right? So it combines a cursive handwriting recognizer and similarity-based matching. So for each unknown gesture, it asks the cursive handwriting recognizer to recognize it. It's using a language model that is dynamically constructed based on the data on the device. At the same time, the unknown gesture is matched against the gestures that have been used by the user and other users. Like that's a crowd. So if the intended target is not in the matches returned by the system, the user has to manually identify the target. But every time the user interacts with the system, it learns from the user behavior. So it gets smarter and smarter. So collectively, there's no magic. But to each individual user, sometimes it works like a magic, right? It can guess the meaning of the gesture without you to tell the system what the gesture is. Okay, I guess I forgot to show these. So basically, this part is it's a crowd-powered recognition. The other part is this part. Oops. This part is the cursive handwriting recognition. So this is a quick demo about how well the system works. As you can see here, we can draw cursive handwriting. It's arbitrary symbol. Okay. Any questions so far?
Like I can imagine that drawing a bee is probably faster than drawing a bird, right? Like how much more useful is this over just like drawing over some convention like just the cursive handwriting?
Yeah, I think you're asking about another metric, that is how efficient it is from the articulation point of view. I think that's certainly one factor. But another thing here is learnability and how natural it is to the user. But just to your question, yeah, I think you're right. Sometimes alphanumerical gestures will be much easier to draw than graphical gestures. But the point of this work is that we want to make sense of whatever the user draws, right? So this is just based on like 20-some participants. Imagine when we reach some critical mass, we can make sense of many things, right? Cool. So this diagram here shows the amount of contribution each prediction source had. As we can see here, initially matching unknown gesture with the crowd gestures and the cursive handwriting recognition played a very important role. As the system sees more and more gestures from the specific user, matching with the user's own gesture gradually became the most important prediction source. So what is important here is that at the very beginning of the experiment, before the system has observed any usage from the user, it was able to guess the meaning of the gesture 77% of the time, right? So it significantly reduced the user effort and bootstrapped the performance of the system. So we took this crowdsourcing powered recognition further by developing a general platform for generating recognition techniques. Briefly, the idea is that the developer can describe a recognition task in this platform called Crowd Learner. It then distributes the recognition task to mobile workers. So as the data comes in, Crowd Learner continuously trains the recognizer whenever the recognition accuracy falls below a threshold. So the compelling result we got from this work is that a developer can get a usable recognizer, such as the one for recognizing hand-drawn symbols, with less than $10 and under 2 hours.
So does this ask people to install your app?
Yes, so mobile workers, they need to install a client on the phone.
So next I'm going to talk about multi-touch input. Probably it's the most important class of input behaviors on mobile devices. So it's amazing how many multi-touch gestures are actually enabled in a mobile application such as maps. So these gestures are intuitive and efficient to use, but they're very difficult to program manually. So when it comes to interactive computing, there are always two important problems to address. One is to identify the target object the user wants to manipulate. The other is to determine the operation the user intended for the object. For traditional graphical user interfaces, these can be easily achieved with a precise input device such as a mouse and a set of well-defined interaction events such as clicks and drag and drop. But for multi-touch UIs, it's often quite tricky to address these issues. For example, when we land our fingers on the screen, it's often ambiguous to the system which object we try to manipulate. For example, as we can see here, one of the fingers actually partially landed on the cameras underneath the photo. So another factor here is that so rich interaction semantics of multi-touch gestures are often expressed through complex finger transitions and continuous motion. It's hard for developers to program them right in their code. And lastly, so one big advantage of multi-touch input is that a user can perform multiple actions at the same time. But it's hard to for the developers to manage these parallel operations based on the traditional event processing framework.
Why? I mean, if these are all truly independent objects, then they're just firing off independent listeners. Why is this difficult?
So basically, you have to dispatch events to different actions.
Yes.
So I think you can certainly do it, but it's going to be complicated for you to manage the all the events and because each of these actions will have its own state, right? So it often results in a complex state transition diagram.
I would buy it if, maybe I'm misunderstanding. I buy this if there are relations between multiple things that are happening. So, you know, imagine on a traditional desktop computer, if I attach using jQuery or something, a drag event over here and a drag event over there, you know, they could in theory, although JavaScript's typically single-threaded, they could in theory just sort of run in separate threads and react to the drag events individually. But it seems like maybe what you're getting at is that it's difficult if I'm like if I need some behavior that involves dragging these two together to create a pile or something like this, where like now you have these independent listeners that have to trigger some joint inference. Is that what you're getting at?
I think so. The situation here is that if we dispatch events deterministically, like what you described, then it becomes two independent problems. Then it's much easier, right? So what's complicated here is that for multi-touch input, the dispatching of the events often is not deterministic. Like so, the event for so there's some chance that the event for one action, it might be actually for a different action. I think it's more to do with event dispatching part. But I think you're right. When there's interaction between two behaviors, it becomes complicated.
Keep going, and I'll continue stewing on this.
So to address these problems, my interns and I have been developing advanced tools for developers to easily program multi-touch input in their applications. We want to transfer what programmers have learned from programming GUIs to multi-touch interaction. So next up, I want to show you how this tool actually works. Here, let's assume we want to add some multi-touch behaviors to our to this photo album application. So we start by adding a gesture library to the project. This is a typical Android Eclipse setup. So this will bring up our gesture creation tool. We can directly demonstrate the target gestures. These common gestures can be recognized by the system and automatically added to the gesture set. That's the top left part of the screen. So if all we need are these common gestures, in less than 20 seconds, we have created our gesture set. But if we want a new gesture, something has never been seen by the system, like this three-finger pinch is recognized as a three-finger swipe. Now the developer can give it the right name, three-finger pinch, or pinch with three fingers. The system learns from that gesture. From now on, it can correctly recognize 3-finger pinch. So that's how we can add a new gesture to the set. So the gesture set has XML specification automatically generated. Here we can finely tune each gesture. For example, we can specify temporal and spatial constraints for these gestures, such as the time interval between two taps for double tap event. A question? So once the gesture set is created, it's available to the project as a type of a resource, just like layouts and images. We can directly reference. We can treat these gestures as a high-level events and reference their names in the code. So our touch framework is designed in a way that it can be easily integrated with the existing event framework. As you can see here, we can attach gesture event handler to any object we want to have gesture behaviors. It's very similar to actually how we program GUI interaction. With these, we have added a set of multi-touch gestures to our application. We can perform all kinds of multi-touch behaviors. So we can manipulate the photo and the underlying canvas. We can transition from one behavior to another without lifting out the fingers. So we can also create a photo group by selecting a collection of photos. We can then manipulate the collection as a whole. Each individual photo within the group remains interactive. So all these rich behaviors can be easily implemented with this tool, with the system actually handles the complexity underneath. So we asked 8 professional programmers. You have a question?
The demo you showed before, does it handle the challenge you presented before, where if you try to do two different gestures simultaneously, it handles both? If you try to rotate one picture while moving another one, would it recognize that?
Yes. So it tries to. So that's so it basically, as the slides I'm going to cover later on, basically. It has a model to capture parallel operations, yes. But it's not shown in that video. Yeah. So we asked the 8 professional programmers who had Android experience to use the tool to enable multi-touch behaviors for an application. On average, it took them about 20 minutes to finish the task. We also compared so our condition with the baseline condition when our tool was not available. Then none of the participants could actually finish the task. So this comment was made by one of the participants when they suddenly realized the complex event transitions they have to cover in the code, which is not something they could finish in the time allowed in the experiment. Yeah. Why did that come up? So now I want to talk a little bit about the important technical details underlying this tool. As I mentioned earlier, there are 2 important factors we want to cover. we want to address. One is the target interface object. The other is the intended operation or gesture here. So we use the two random variables to capture these two quantities for probabilistic inference. The dependency between these two variables here captures the semantics that an interface object determines what kind of gesture behaviors should be available. So then we designed our model based on a dynamic Bayesian network that infers the current interface object and the gesture from a sequence of raw and touch events. So the part of the model captures the semantics that how well the observed touch events actually match a given object and gesture. For example, how well the touch event falls in the boundary of the object, and or how well the continuous motion of touch events demonstrate the transformation required by a gesture, such as scaling for the pinch gesture. So the other part of the model is about how the past interaction state actually influences the current state, right? For example, for a single tap event, we expect the finger to be lifted after the finger goes down. So the model seems quite complete in terms of capturing all these factors that determine the interaction state. I'm going to talk a little bit about how we can create such a model, right? So there are two stages. When we create a gesture set, the system automatically generates an inference model for each individual gesture, either based on the demonstration or the XML specification. Then, depending on how these gestures are actually allocated to interface objects at the runtime, the system instantiates and assemble these individual inference models to form a global model. So here, this plot shows how well the system can recognize a set of multi-touch gestures. As we can see here, the more touch movements the system sees, it can better recognize these gestures. But with multi-touch interaction, we often want to make decisions as early as possible, right? So we don't want to wait the entire gesture is finished, then we decide what the user is actually doing. So as you can see here, the number of gestures in the set, it actually tells us something about how hard it is to separate these gestures. But we want to develop a more precise measure about ambiguity of the gesture set. Any questions so far? So we developed the measure about the ambiguity of the gesture set by looking at how the inference model of each individual multi-touch gesture is different from each other in the set. I'm not going to talk about the measure here, but the scatter plot here shows the effectiveness of our measure. As you can see here, it's actually the disambiguity. I put ambiguity here. It's really disambiguity. So the disambiguity here is negatively correlated with the amount of touch events the system has to observe to reach a target accuracy like 90% correct. So what we can get from this is that we can learn a linear predictor to tell us how much touch movement will be needed to reach a certain accuracy. This actually translates to how quickly the system can resolve the ambiguity and the response to the user input. So far I have talked about interaction modalities in the foreground. It's equally important for us to learn from user behaviors to leverage the contextual input to optimize the UI. So for this, I'm going to talk very briefly about my recent work on mobile event prediction. So predictions are useful in many cases. For example, we can reduce the clutter of the home screen by only presenting applications that a user is likely to launch next. Likewise, we can predict context for speed dial and dish options for ordering based on the user's past behaviors. But the current problem here is that developers often need to develop prediction components for each of these applications, right? So it involves a lot of technical expertise, such as machine learning, and it introduces repetitive engineering effort and with mobile computing resources. So more importantly, these isolated prediction models can only see the user behavior that happens within the application, while interaction behavior often interaction behavior often has something to do beyond a single application, right? So it's often situated in a much larger context. So to address these problems, I took an infrastructure-based approach by developing an on-device prediction service. It learns from the interaction events as reported by each application and predicts what the user is going to do, what actions the user is going to do for each application. So internally, the service learns a prediction model for each application by combining a set of well-defined features using an online learning framework. So all these prediction models are not isolated. So they actually take into account how the behavior in one application is related to the behaviors in other applications. The experiment I did by evaluating the service with two large-scale data sets indicated that using the cross-app behaviors can significantly improve the prediction accuracy. So that's all what I want to talk about for this work.
I think are those actions that you're tracking that are a little too small for me to see, are they generic actions that are registered across the entire device, or do the applications themselves publish events that would be specific to the application? Like in the speed dial app, maybe there's like a contact selected event that's observable.
So all these are application specific events.
And is there some requirement in the Android SDK that makes these events observable to you? Or does the application developer have to add them?
That's a good question. So the programming paradigm here is that it's up to the application to report what has actually happened in the application using this send API. So
shoot up a flare whenever the user does something interesting, and then your app takes care of.
Exactly. So it sends interaction events of interest to the service, and then later on it can actually query what the user is going to do at this point. Yeah. So so far, all the examples I have given to you is regarding a single device. But as mobile and wearable computer gadgets actually become ubiquitous and diverse, it's quite common for a user to perform a task across a range of devices. So I want to give you two examples of what we have been doing on the cross-device interaction.
Though mobile devices are becoming very powerful, their small form factor means that collaborating or sharing information with someone else is a turn-based experience. We present OpenProject, a highly scalable web-based framework for sharing mobile application on a remote display using an intuitive projection metaphor with only the phone's camera. Let's say Ben wants to show Angela a photo. To project the Image Gallery app, Ben aims the phone's camera at a QR code that identifies the display. Once identified, the QR code turns into a checkerboard pattern. This checkerboard automatically moves to follow the phone's motion, emulating a projector-based solution. Ben can also scale up his projection by gesturing in a counterclockwise fashion. Once Ben is satisfied, he can affix the projection and put the phone away. At this point, Ben and Angela can flip through the photos either on the phone or even on the touch-enabled display, and their changes will be shown in real time. OpenProject allows users to collaborate around larger surfaces in tasks such as sharing media or navigation tasks. A touch-enabled remote display even enables physical multiplayer mobile gaming. Everything runs natively on the phone, but is projected on any display that can run a browser window. Additionally, OpenProject needs no external hardware to simulate a handheld projector. Our robust tracking algorithm uses a single marker to track a user's motion with only the built-in camera. OpenProject was designed to be easily deployed on a large number of low-powered mobile devices and remote displays. Android developers can enable remote sharing of their applications by adding our lightweight library, which performs all the work locally on the mobile device. Moreover, our web library enables streaming of multiple mobile devices' screens on any number of displays without performing any complex computation. Combined, the architecture provides a highly scalable solution that eliminates the need for complex hardware powering servers and remote displays. We evaluated OpenProject through a number of
Weave is a framework for developers to create cross-device wearable interaction.
So, any questions for the first video? I can just show the last one.
Scripting. Developers can program and test cross-device behaviors using Weave's web-based integrated authoring environment. Here, a developer creates a new service and edits it in the Edit panel. The developer selects a device with a shareable display in the script. Weave's abstractions allow developers to focus on their target interaction behaviors regarding the device's capabilities and affordances. In the Layout panel, the developer adds an image element in HTML and specifies to show it on this device. The developer then chooses another device with a small touch display and adds 2 buttons to it for photo navigation. By adding a callback function to event tap::button, the script now allows the user to go forward and backward through the image list on the other display. The developer tests the interaction with the emulators. When ready, the developer adds real devices to the Weave network for live testing. The developer deploys the scripts to Weave's runtime environment on an ad hoc network of devices. With minimal effort, Weave creates a range of rich cross-device behaviors. By adding just a few more lines of code, the developer enables a new interaction mode of swiping on smart eyewear. Here are some more use cases. With this script, a launch pad on a wearable device launches native applications on the phone. The All mode invokes a callback function when a specific event occurs on all of the selected devices at the same time. For example, this script enables multiple users to join a group by physically shaking their devices at the same time. The combine operator combines several event types from multiple devices. Here, a cross-device pinch gesture is detected to zoom in on a photo.
All right. So lastly, I want to thank the interns who have worked with me over the past few years. I only got a chance to show some of our projects. If you want to know more about our work, come to visit my website. Thanks.
We have a couple minutes that are available for sort of any questions you've been holding on to or open-ended discussion.
So I was thinking about the context sensitivity that you were talking about. Have you thought about the building sort of a closed loop into that? So if you walk into the supermarket and it knows where you are, so it then goes and brings up information that's relevant?
So are you talking about the application scenario? Like if we know...
Application scenario, location-specific information or reconfiguring the device in such a way?
Yeah, I think so. A lot of work has been done in the field of for location-based or location-enhanced interaction, location-based interaction. So I think that's a typical scenario actually people often use. Like if you go somewhere, the application should bring up location-specific information. So yeah, I think that would be a good example. But I'm not sure if I have answered your question.
That answered my question. And the follow-up is, has anyone looked at emotion-based reconfiguration? So if the computer could go and read user state?
Yeah, actually, that's a good point. So I think a lot of work actually is going on in that regard. I think there are all these sensors trying to detect your emotion, stressness, anxiety. But so far, a lot of applications are focused on health-related things. But I think by knowing all these things, we can certainly improve interactions in some way, right? So, but not many applications, I mean, beyond health, are actually out there. I haven't seen many.